Models versus algorithms, LCD algorithm for addition. How do we find a lowest common multiple? Any suggestions? We had at least 3 techniques we went over back in chapter 4.
Could we use the tree?
Yeah, we could make a factor tree, and the point of that is to try to find the prime factors. So, oh, there's something in the chat. Multiply them together. So we could multiply them together. That would give us a common multiple, but not the lowest common multiple. So we want to find the lowest of any common multiple, and the product of the two numbers is not necessarily the lowest one. But there is a strategy we could apply where we multiply them, but then we need to know the greatest common divisor. So 10 is equal to 2 times 5. 2 and 5 are prime, so it doesn't factor further. And then 15 is equal to 3 times 5. 3 and 5 are prime, so that doesn't factor further. The LCM of these two numbers for factors for the 10 has to have a factor of 2, has to have a factor of 5. For 15, we also need a factor of 3. We don't need another factor of 5 because we already have one. So the LCM is going to be 2 times 5 times 3, or 30. If I multiply 10 and 15 together, then I'm going to get 150, which is significantly larger than 30. And again, I'm trying to find the lowest one possible. So the first step in applying the LCD algorithm is finding that lowest common denominator, which in this case is 30. So that's step 1. What's step 2?
We have to make our denominators 30, so then we would have to multiply the numerators and the denominators.
Okay, so how do we figure out what to multiply by?
So 10 times 3 would be 30.
Okay, so how did you figure out it was 10 times 3?
Because 3 tens makes 30.
Yeah, so ultimately we have to guess, what do I multiply by 10 to get 30, which is a division problem. So the second step to get those multiples is 30 divided by 10 is 3, and whether you do it by guessing at multiplication or division. So Amy's strategy was to think, what do I multiply by 10 to get 30? And she thought 3, which is a division problem, right? And we have to do the same thing for the other number. We have to say, okay, if I take 30 and I divide by 15, that is 2. And in other words, what times, let's use a different color. So the other strategy is the what do I multiply by? What do I multiply by 15 to get 30? Okay, so we got to think hard about that. So that's the second step. I have to find those multiples, and the third step would be to apply them. And so then I take 3 times 10 and 3 times 3. I take 2 times 15, and I take 2 times 4. 4 times 2. Send that backwards. So the fourth step is where we finally get to do the addition. And so we have 3 times 3 is 9, 4 times 2 is 8. The common denominator is 30. There's no need to write that again. 9 plus 8 is 17. 30ths. So the LCD algorithm has multiple steps. One, you have to do a significant amount of work to find the lowest common multiple of the denominators. Once you find that, you got to figure out what you multiply each denominator to end up with that. And once you do that, you actually have to act on it and then do the addition. So there's essentially 4 steps to it. What's the LCM? What multiples do you need to get your common denominators? Then finally act on that and add the numerators from the common denominators. Okay. So that's an algorithm. Question: why do we have to have a common denominator? That's what the model answers. Why do we need common denominators? Why can't we just do something like, say, let's go to a new page. Why not take, what was it, 3/10 and 4/15 , and say 3 plus 4 is 7, and 10 plus 15 is 25, and say, yeah, let's let the answer be 7/25. That's way easier. Why don't we just do that instead? This is much easier. Why can't I do this?
Fractions are equal parts of a whole, so we have to have equal parts.
Okay, and 10s and 15ths aren't the same thing. Yeah, good. So there's two pieces to the puzzle as to why this is bad and this craziness is good. It's because number one, add means combine and count. And two, count, there we go. As Amy said, fraction's an equal part of the whole. And when we take those two things together, we can't directly take 3/10 and add that to 4/15 because a 10th and a 15th are not the same thing. These are not equal parts. And so the first step in our modeling is to figure out, well, how do we go about finding a common denominator? And that kind of went back to something Mansi meant earlier. It's like, let's just multiply the two denominators together. And I don't want to do that with 10ths and 15ths because the drawing is too messy, which is why we were working with things like halves and thirds and fourths. If we look at an easier problem like 2/3 plus 1/4, here I can much more easily draw what 2/3 means. And 3/10 isn't that hard to draw, and 4/15, but if we do the whole cut each like the other, I don't want to draw cakes with 150 pieces. And I think you don't want to draw that either. That would be like punishment for something. Math should not be punishment. And again, I find it a nice strategy to cut the cakes perpendicularly to each other, because then cutting each like the other, I think just makes a little more sense. So as far as my 2/3 go, here's one of my thirds, and this one can be my other third, and then my fourths. Let's pick this one for the fourth that I'm going to keep. And we can see these pieces aren't the same size. The thirds are a little bit bigger than the fourths. So we can't just say we have 3 pieces because they're not equal sized pieces and they have to be equal sized pieces. So that's when we cut each like the other. So these are not equal pieces. So we can't add yet. All right, so we have to recut like the other. And so I'm just going to draw that separate. So I had my thirds and I had my fourths. And I use a different color to cut. Let's use blue. So that this one needs its fourths and this one needs its thirds. Now I have equal sized pieces. I have 12ths to work with. And here I can see it's 2 by 4, so there's 8 12ths there. And this is 1 by 3, so there's 3 12ths there. Now I have like pieces, so I say, oh yeah, 8, 9, 10, 11, there's 11 12ths there. And often it's a good idea to just double check that there's no way to reconsolidate these for a slightly better answer by putting them together in one cake. So let's put my thirds in and my fourths in, and then count up the pieces I have. I have 8 here, so oops, that's not my highlighter. So 1, 2, 3, 4, 5, 6, 7, 8, and then my 3 more, 9, 10, 11, and I have 1 extra. And no matter how hard I try to regroup here, if I group by 2 or 3, I'm always going to have something extra. And so the 11/12 is not going to reduce. So that would be the final answer. Because we can play around and find that there's no way to regroup. Okay. So why do we have to have a common denominator? Well, a fraction has to be an equal part of a whole. If we don't have equal parts, we can't add, because add means combine and count. How can you combine things that aren't equal and count them up? The best you can say is, hey, there's 2/3 there and there's 1/4 there. Until we chop them up into the same size pieces, we can't regroup them together. So a model explains why something works the way it does, and an algorithm just shows us how to get an answer. It doesn't explain why, it's just do it because I said so. And Monsi had mentioned another great algorithm, which is just multiply the denominators, and that's the arrow algorithm for addition. And the arrow algorithm for addition is nice because it just basically skips the LCM stages 1 and 2 here of this algorithm. It says, that's a lot of work. It's just easier here with the 3/10 and the 4/15. We're just going to get a quick denominator by saying, hey, 10 times 15, that's not bad. That's 150. 15 times 30, that's a little harder to calculate, but we have 15, 15, and 15, and okay, yeah, I can do that. That's 45. 10 times 4, that's too bad. That's 40. Remind myself I'm adding here as opposed to subtracting, so I get 85 over 150. And then I reduce if necessary. So how do we reduce this? Well, we might notice that top and bottom are divisible by 5. And when you work with kids, you should definitely write out, I'm dividing the top by 5, I'm dividing the bottom by 5. And then we have to figure out how many times 5 goes into 85. So let's see, 5 goes into 8 once with 3 left over. 5 goes into 35 7 times. And then in the, oops, I have to draw my arrow there. 5 goes into 15 3 times, and then with a 0. So there's 17/30ths. We had to reduce to get there. So pros and cons of these algorithms. Well, let's see. Pro with the LCD. I had the smallest denominator. That's a pro, 30. Okay. Con. Finding the LCM was tough. It was a bit of work, and then I had to come up with those multiples, then I had to multiply them in. So there's a lot of steps involved here. Pros and cons of the arrow algorithm. Well, pro, it's pretty easy doing those arrows and multiplying stuff. And then I added, and I had to reduce. Okay, so I had to reduce here, but not with the LCD. Is that always a pro of the LCD that you never have to reduce? What do you think? Let's check. Pick a different problem. How about, let's do 3/10 again. And then how about 5/14? So if you could do me a favor, what I'd like you to do is apply the LCD algorithm to this. I would like you to apply the arrow algorithm to this, and then we'll look at the differences. So please make each calculation on your own, and then we'll go over it together. All right, so here's some of my work. I'm not quite done. So I started doing the arrow algorithm work. I prefer it because I don't mind reducing, and I like drawing arrows. I think it's fun. So with the arrow algorithm, right, I said 10 times 14 is 140, so that's my new denominator. 14 times 3, I had to think about for a minute. 14 and 14 and 14, I got 42. 10 times 5 was 50. 42 plus 50 gave me 92. And then I looked at this and said, okay, well, they're both even, and I didn't get to this part yet, but I was about to. And so I said, all right, I better divide by 2, top and bottom. And I strongly suggest we write that out to be clear what we're doing. Otherwise, it's easy to make a mistake. Half of 92 is 45 plus 1, 46. And half of 140 is 70. And they're both still even, so I can divide by 2 again. And, you know, afterthought is, oh, I could have divided by 4, but I didn't see that. I didn't know 92 was a multiple of 4, so 2 seemed easier at the time. Half of 46 is 23. Half of 70 is 35. Can I reduce further? Well, I don't know. Let's see. They're not even. 3 doesn't go into 23 or 35. What's next? 5 goes into 35, but not 23. What's next? 7 goes into 35, but not 23. I'm done. Okay. So I checked multiples related to the bigger number. Nothing reduces here. That's the final answer. For the LCD algorithm, I had to think, okay, for 10 and 14, I need their factors. So 10 factors is 2 times 5. 14 factors is 2 times 7. So the LCM, lowest common multiple, is going to be 2 times 5 for the 10. For the 14, well, I already have a 2 in my 2 times 5. I just need a 7 in there. I don't need another 2. And then, so that's 2 times 5 times 7 is 70. And then now I'm thinking about, well, what am I multiply by 10 to get 70? And I was thinking, okay, 7 times 10 is 70. What do I multiply by 14 to get 70? And I had to whip out my calculator to see that 5 times 14. And the 7 and the 5 were right here. They were the uncommon factors in the LCM. And so I had to multiply this by 7 over 7 to get my 70 in the bottom, this one by 5 over 5 to get my 70 in the bottom. So then I just rewrote the 70 in the bottom. 7 times 3 is 21, 5 times 5 is 25, 21 plus 25 is 46, and oh darn, they're still even. I can divide by 2. So maybe I made a mistake. Maybe 70 is not the lowest common multiple. Because now that reduces to 23 over 35. Maybe 35 is the lowest common multiple. Let's see, does 10 go into 35? No. Does 14 go into 35? No. Okay, so 35 is not the lowest common multiple. 70 definitely is, but it reduced anyway. So even with the LCD algorithm, even though we have the smallest possible denominator to get the fractions added, we still have to reduce sometimes. Is that an argument that it's not worth doing the LCD algorithm? No. I'm just going over pros and cons of the two of them. Although I have the smallest denominator, I still have to reduce sometimes. Sometimes I don't. Arrow algorithm, more often you have to reduce, but sometimes you don't. It depends on what the fractions were. All right, so algorithms. There's no explanation of why that should be the answer or why we should follow that steps. An algorithm is just a bunch of steps you follow, and when you're done, you got some answer. A model is where you say, okay, this is what it means to add, subtract, or multiply or divide, and this is what the things we're adding and subtracting. Let's use those ideas to try and figure out how to get an answer. So the models always lead to algorithms. And this is important on the test. I need to know that you understand the difference between a model for a certain operation versus an algorithm for that operation. All right, so let's try another. Any questions, by the way, about how the arrow and LCD algorithms are different but alike? So I talked more about the differences. How are they alike? Any thoughts? Did we have to find a common denominator for both of them? Yes, we did. Okay, so that's how they're alike. What else? we have to reduce sometimes for both of them? Yep, that's true too.
But that's not always going to be the case where you have to reduce, I'm guessing, right?
Yeah, because the denominator tends to be bigger with the arrow algorithm, you'll end up reducing more often than you will with the LCD algorithm. But you still have to reduce sometimes with the LCD algorithm. So then the question becomes, you know, what you're going to have to teach the LCD algorithm in the future. It's in textbook. Kids are expected to understand it. It is an important thing in algebra for the kids that need to go on to algebra. So we definitely need to help kids try and learn it, but there are lots of kids that are just going to stumble during these first steps right here. And so it's good to have a backup and say, all right, well, let's forget about that part here. Let's just do this. And then the reducing part, that's not too bad. I think reducing is easier than finding the lowest common multiple of the denominators and then adjusting them. I think that first part's harder. All right. Let's see what else. Oh, I know what else I wanted to mention based on a comment somebody made earlier. Let's go this way. Relationship between the lowest common multiple of two numbers and the greatest common divisor. And finding the lowest common multiple is a lot of work. We have to either list the multiples or we have to have prime factorizations to find them. And GCD is pretty similar. So let's just play around with the two numbers we had a moment ago, and they were, let's say 10 and 14. And 10 we know is 2 times 5, and 14 is 2 times 7. And the strategy, there's two strategies for how to select those factors for the lowest common multiple. One strategy is you just say, okay, pick a number like 14. 14 has to have a factor of 2 and it has to have a factor of 7. Without those two factors, you don't get 14. Then you look at the other number and say, okay, am I missing anything? 10 needs a 2, but I already got that covered. I don't have the 5 yet, so I got to put the 5 in there. And so we just choose the minimal set of factors based on the ones that we have, and it doesn't matter which one you start with. The other strategy we had for the LCM is that we choose the lowest power of the common factors. The powers here are 1, 1, 1, and 1. And so the lowest power of 2 that I see is 2 to the first, or 2. The lowest power of 5 that I see is just 5 to the first, or 5. And the lowest power of 7 I see is 7. And so that's another strategy for selecting the right factors to make the lowest common multiple. And so then I multiply them out and I see, oh, okay, it's 140. GCD is a slightly different thing going on. We still need to know those factors, but we want to know what divisors, what factors do they have in common. And I can just look here and see, well, as far as the common factors or common divisors go, they have a 2 in common, and that's it. And a trick to finding the LCM is that for any pair of numbers, so let's call those numbers A and B, if you multiply those two numbers, you get the same answer as when you multiply their LCM and their GCD together. So let's suppose I was struggling with this LCM strategy, but the GCD strategy was easier for me. All I have to do is multiply the two numbers, 10 times 14. I'm not sure what the LCM is, but I know the GCD is 2. So if I just divide the 2 to the other side, then what's left has to be the LCM. So 10 times 14 is 140. 140 divided by 2 is 70. So 70 has to be the lowest common multiple of those two numbers. So if you didn't like the strategy of using the prime factorization to find the LCM, you have to find the GCD, and then the LCM is always going to be the two numbers multiplied divided by their greatest common divisor. Which was a trick I went over way back in the beginning in chapter 4. So that's a nice thing to know as far as another strategy to work with. All right. Next. I think division is what we've worked on least, so let's talk about division a little more. So again, we have two different things. We have models for division versus algorithms for division. An algorithm is just a set of rules or a rule that you follow. A model is why do we do it the way we do it. Models for division are repeated subtraction, at least with fractions, and what I call groups in, which is related to long division. And we'll take a look at both of those in a moment. Algorithms, we came up with a few algorithms. One algorithm is to multiply by the reciprocal. And then two, I showed the common denominator algorithm. And then three, there's the arrow algorithm. And why does multiplying by the reciprocal work? Why does having a common denominator work? Why does the arrow algorithm work? All of the whys behind these here are answered over in these models. So these guys answer why. This is just how to do it, right? Just do it because I said so. So the repeated subtraction, suppose I had, let's do 3 divided by 1/2. So we'll just do an easy version. And repeated subtraction just says, well, how many times can you subtract the divisor from the dividend? So how many times? Subtract 1/2 from 3 to get to 0 or close to 0. And it's just a matter of repeatedly subtracting. You just start subtracting, see how many times it happens. So 3 minus 1/2 is 2.5. And 2.5 minus 1/2 is 2. And 2 minus 1/2 is 1.5. And 1.5 minus 1/2 is 1. Just keep going until we're done. 1 minus 1/2 is 1/2, and 1/2 minus 1/2 is 0. So I finally get to 0 after 1, 2, 3, 4, 5, 6 subtractions. So according to this, 3 divided by 1/2 should be equal to 6. Checking the denominator, the algorithms for that, if I try algorithm 1, it says multiply by the reciprocal. So 3 divided by 1/2 is 3 times 2, and 3 times 2 is 6. Why did that work? Well, because it worked over here too, and this is what division means. There's not too much to it besides that. 2, common denominator. I would view that as 3 over 1 divided by 1 over 2. Common denominator would be 2. So if I multiply top and bottom here by 2, that's going to give me 6 over 2 divided by 1 over 2. And then the algorithm says ditch the denominators. What's 6 divided by 1? And the answer is 6. So I find the common denominator, and then I toss it out, and I just divide the numerators. But I have to have a common denominator first in order for the numerators to make sense. So that's an interesting algorithm. And then 3, the arrow algorithm, I would view that as 3 over 1 divided by 1 over 2. And here the arrows flow backwards and diagonally. So 1 times 1 is 1, 3 times 2 is 6. 6 divided by 2 is the answer, or 6 divided by 1, excuse me, is the answer, which is 6. So those are the 3 different algorithms. No pictures, no explanation, just do it. That's an algorithm. Models, the groups in, we'll do a couple versions of that one. 3 divided by 1/2 equals what? So here, I need to know that division means groups in. Oops, I can spell division today. And then I have to interpret what that means. So this means how many groups of 1/2 are in 3? Okay. So in other words, 1/2 goes into 3, how many times? So it's nice to see what a half looks like and what 3 looks like. So I could draw a little cake here and say there's half of my cake. And then what 3 looks like, so I would have 1, I want to try and make the same size hole there, cake, 2, 3, oh boy, they got progressively bigger, didn't they? And I might as well split them in halves, so it matches. And again, I'm looking for groups that look like this one here. And I see 1, 2, 3, 4, 5, 6 of them. So 1/2 goes into 3 6 times because I found 6 groups of 1/2 in 3. And so those were the 2 models, repeated subtraction, which is really a lot like the groups in. The groups in is just kind of like a physical version of the repeated subtraction. And thinking about that reciprocal thing again, like this is kind of, and you can kind of see it in this picture right here. According to the multiply by the reciprocal algorithm, 3 divided by 1/2 is the same thing as 3 times 2. 3 groups of 2, those 2 groups of 2 are the halves, right? So here's a group of 2, here's a group of 2, here's another group of 2, right? There's my 3 groups of 2 down there. So it's just another way to think about how those fractions fit together, multiplying by the reciprocal. All right, how's it going out there?
Good.
Okay, so we took a look at addition again, division, which tends to be pretty tricky. Let's look at subtraction and then multiplication. And again, let's compare models versus algorithms. As far as models for subtraction go, our main models are takeaway or comparison. Oop, why did I put a 3 there? That's weird. Comparison. Algorithms, not too much different than addition. We have the LCD algorithm and we have the arrow algorithm. And let's try, let's see, a relatively easy example. Let's do 2/3 minus 1/2. So this would, for the first interpretation, I could say, well, let's take 1/2 away from 2/3. And so to do that, I have to see what 2/3 looks like. So here's my 2/3 there. And I want to take 1/2 away. And so got a couple options on how to do that. Let's use green. Since I don't see a full half here, then I might want to rebuild this a little bit. So I tend to like to cut in the other direction so I can see what a half is. And in the top and the bottom, I don't have a full half. But what I could do is I could pick up one of these pieces and move it so I could see the half. So I'm just going to redraw this a little bit to show the takeaway. Oops, I switched my colors accidentally, kind of. And so what I'm going to do is I'm going to leave that one there. I'm going to leave these two down here. But I'm going to take the piece that was here. I'm just going to put it down here so that I can see the half carefully. And so now I can make a note to myself that I need to take that away. And then that leaves just this single piece here. Myself not much room to do this. Let's squeeze it down here. All right, so that leaves that just that 1/6 of the whole. So I did have to find a common denominator because I had to figure out how halves and thirds fit together. Are there other ways you could draw this to illustrate it? Yeah, there's lots of ways you can improvise. I kind of like the perpendicular cuts because I can do it consistently with any kind of a fraction problem. An alternative there, I don't know if any of you were thinking this or drew this when you were playing with these. So trying to do, again, 2/3 minus 1/2, thinking about takeaway. And this one, I don't know, I think it's a little bit harder in some ways. So here's my 2/3. And then I want to think about half to take away. And maybe since I cut vertically the first time, if I make a vertical cut right down through there and say that's the halfway mark, and I'm taking this away, how do I figure out what that piece right there is that didn't get taken away? Right, all this stuff got taken away there. So I have to figure out what that means. And I think it's just a little more obvious what it means when I make that horizontal cut there. So I'm going to leave that like that. The comparison is pretty similar. Oops, upside down. 2/3 minus 1/2. What does comparison mean with fractions? You should write that out. And this was something that I noted a bunch when I was grading your activities. Whenever I do these, I speak and write my explanations as I go. So you got to make sure when you draw pictures, you have some explanation to go with them. So I'm going to have an explanation up front and then an explanation after. What does comparison mean here? It means how much bigger is 2/3 than 1/2? How much more is 2/3 than 1/2? Well, in order to see that, I have to compare 2/3 to 1/2. I got to see them next to each other. So again, like before, I draw my 2/3. And I draw my 1/2 next to it. So I want to compare them to each other. Again, I like to draw them perpendicular in terms of the different cuts. And I'll show my 1/2 shaded. And maybe up front, it's not clear that this is bigger than that. And so these are different size pieces. So it's unclear, the relationship. So then we recut each like the others. And a lot of times we'll recut on the spot, but I'm going to draw it in stages just to help better illustrate the sequence of events here. And whenever possible, I like to recut with a different color to compare to the original. So let's recut in red, halves, oops, that's not red, try again. Red that way for halves and red this way for the thirds. So now I can see this one has 4/6, this one has 3/6. And so there's 1/6 more in the 2/3. So then 2/3 is 1/6 more than 1/2. So a little explanation up front, a little explanation during, and a sentence kind of state the conclusion there. So comparison, picture's a little bit more work than takeaway, but I think it's more clear what's happening with the comparison. So that's my preference in how to model the answer. And we couldn't do the comparison without having a common denominator because we had to see the same size pieces. So just a note here, we need same size pieces to make a comparison. And that same size means common denominator. So those are the main two models for subtraction. Algorithms, again, same ones we had before. We have the LCD algorithm and we have the arrow algorithm. So LCD algorithm is kind of the same thing as the arrow if the lowest common multiple is the product of the two denominators. So you're really not going to see much of a difference. So 1 for the LCD, 2/3 minus 1/2. The lowest common multiple of 2 and 3 is 6, which happens to be 2 times 3. All right, same factors, nothing extra. So this one's pretty straightforward. Oops, I did something wrong. 4 minus 3. And so there's my 1/6. So that one wasn't a lot of work. The arrow algorithm, I'm having a hard time saying that today. 2/3 minus 1/2 is that multiply the denominators and cross multiply to get the correct numerators. 2 times 2 is 4, 3 times 1 is 3. And remind yourselves that it's a subtraction so you don't accidentally add. And 4 minus 3 is 1/6. So pretty similar. They're identical if the LCM is the product of the two denominators, which doesn't always happen, but sometimes it does. So just a note, if we're subtracting, we need a common denominator. Why? Because of what takeaway means and because of what compare means. We can only take away things that are like, and we can only compare things that are like. Same thing when we're adding, have to have a common denominator. As far as division went, although there is a common denominator algorithm, the arrow algorithm and the multiply by the reciprocal algorithm don't require a common denominator. So division, it just kind of depends. You could use a common denominator, but you don't have to. Addition and subtraction, you cannot add without it. All right, and last but not least, multiplication. Models versus algorithms again. For multiplication models, we have a couple. We've got repeated addition, which we haven't used much, but it works. We've got the idea of groups of, and we have the idea of area, which equals base times height. For algorithms for multiplication, there's pretty much only one algorithm, which is the arrow algorithm. So if you have A over B times C over D, you just multiply. A times C is the numerator, B times D is the denominator. Reduce if necessary, or if possible. The question is, well, why don't we need a common denominator? Well, that goes back to looking at any of these models here. So let's just pick an example. How about 3/5 times 3/4? If I want to multiply. So what does it mean to multiply? You could say this is what it means to multiply, and no, that's not what it means to multiply. That's just how to get the job done. That's a machine. It means either repeated addition, or it means groups of, or it means area is base times height. Now, the repeated addition only works if the first number is a whole number, which I don't have here, so that only works some of the time, not this time. Groups of, that would mean what is 3/5 groups of 3/4. So I'm going to attempt to show that. Now, I can't show 3/5 of something till I know what the thing is, so I got to know what 3/5 is first, 3/4 is first. So I can't show you, and again, the question here, groups of, what is 3/5 groups of 3/4? So first I have to figure out what is 3/4. All right, so I'm just going to draw my cake and show 3/4. And there's a half, cut those in half, and now I can show 3/4. So there's my 3/4. Okay, now of that 3/4, I only want 3/5 of it. Okay, well, easiest way to come up with that is to break this up into 5 groups of 5. So let's make some marks. 1, 2, 3, 4. Yeah, not too bad. So here, are my fifths, right? 1, 2, 3, 4, 5 rows there. So I want 3/5 of the 3/4. So maybe I'll pick this one here, and that one there. So this group right here is 3/5 of the 3/4. Now the question is, what part of the whole is that? Because a fraction is equal parts of a whole. Well, let's see. I have a bunch of little pieces here, and if I count them, let's use a different color to count. How about a yellow highlighter? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 little pieces that I've isolated for the 3/5 of 3/4. 9 out of what? Well, my grid has 4 rows and 5 columns. 4 times 5 is 20. And so I get 9/20ths out of that. Now, I didn't really find a common denominator. I never turned both of these into 20ths. I just used the idea that multiplication means groups of, and out popped 9/20ths. And 9 happens to be 3 times 3, and 20 happens to be 5 times 4. which happen to be the numerators and denominators that I originally started with. Right, so the algorithm, the model leads to an algorithm. So after we repeatedly do a whole bunch of examples of groups of, we see, oh my gosh, the numerators always multiply and the denominators always multiply. That always works, cool. So first we need physical meaning. Once we have the physical meaning, we hope we see a pattern. That pattern leads to an algorithm. All right, so for each of the main operations, addition, subtraction, multiplication, and division, we took a look at models versus algorithms. Model is why do we get the answer we get. Algorithm is how do we do it in general? What's the rule? So that if somebody throws me a more complicated problem, like 23 out of 105, and they want me to add that to 17/50ths, I'm not drawing a picture of that, right? I just need a procedure to get the job done. Procedure is either find the LCD or apply the arrow algorithm for addition. And then I can tell you what the answer is, not too hard. But I'd rather not model that, so we get the model done for smaller numbers so we find the pattern of how the procedure works in general. So that is a summary of sections 5.2 and sections 5.3. Oh, let's take a breath.